All right, so we're ready for our second speaker. Indo's going to talk about JavaScript and Webworkers. Please.
Hi everybody, I'm Ravimbo. I'm a second year PhD student and I'm working with Dr. Vivek Sharkar here. So today I'm going to talk about a little bit about JavaScript, what happens when we try to parallelize JavaScript in browser and where Webworker comes in it. Our specific goal will be to increase performance for virtual reality applications, or more specifically, with virtual reality applications or WebVR, which I'm also going to talk about a little to just introduce you guys in. So first, what this talk is all about. So we're going to talk about WebVR, what is WebVR. We're going to talk about why the performance is important when we try to render it. We're also going to talk about why this is important when it comes to browser and it needs to be responsive. And what are the present ways right now we have and the limitations they have. And then we'll try to talk a little bit about how do we overcome those limitations and about our future work. So first, virtual reality. What is virtual reality? You pop up a headset and you enter a virtual world where you can visit new places, new worlds, or new scenes. How many of you have tried a virtual reality headset before? Awesome. And I'm assuming most of you have tried an Oculus or HTC Vive or a Google Cardboard maybe. And if you have tried more than a year back, the performance may not be that good. It has gone better now, a lot. But all the time you have been using them, you need to use either Oculus SDK to create your games or application, or you need to use their specific ecosystem to build the application. If it's HTC Vive, you need the WebVR SDK, which is part of the Steam now. And if you're using Oculus, you need Oculus SDK to build that. But what if you want to get it out to everybody? There comes the WebVR. What WebVR does is that takes the virtual reality applications out from closed gardens, bring it back to the browser. So you actually create an HTML and JavaScript application which runs in your browser, which is in all of your mobiles and all the devices you have. And you can get a virtual reality right now, right here in your mobile. You can pop it up in your cardboard and it works. You don't have to install anything or anything. So that is kind of the concept of WebVR and why it's taking momentum. So the other uses becomes that when you have you can drop a link which you takes into a virtual world, you can just share immersive experiences to your audience, which is very important in nowadays news and media consumption. So about WebVR. What is WebVR? WebVR is an experimental technology and it's being actively worked upon by Mozilla and Google. And Microsoft recently committed that they are going to have WebVR into their browser, which is now Edge. So in recent future, maybe we'll see WebVR in Edge. But right now, why does it work? If you want to build anything about WebVR, you have to create it according to the specification, which has how you create your application, which lives as a living standard in here in this link. This is a W3C recommendation list, and it's a living spec where you can see and build your application. You can also suggest some changes. That's another reason the work is important, because since this is a living standard, they are ready to merge and improve on the standards. So right now, if you want to consume it, where you can, as of today, it works in Firefox Nightly out of the box. It works in Chromium experimental versions, so you can download a Chromium Nightly, you have to enable a flag, and it works in your browser. It also works in Samsung Internet, and there are mobile polyfills available for older browsers to use with VR. Essentially, if you actually have an Android phone right now, if you have Chrome installed in it or Firefox Nightly, or if you have iOS and you have Chrome inside it, you can actually visit most of the demos I can show, and you will be able to see them in VR right now. Now, what about latency? Now, when we talk about VR, responsiveness is very critical. We need to have an environment where it interacts with you, almost near real time, because you'll be percepting it as a real world. So what are the problems? Few of the problems is that how to determine the tracking position in room scale VR, where you are, if you want to walk around. And the second problem becomes rendering. How fast you can render. There is a time limit before you have to render every frame so that it becomes realistic enough for the user. And there is also a problem that you have to actually make those pixels appear. For today's talk, we are going to only concentrate on the second problem, that about the rendering, how to actually make it fast to render in the browser. So the problem, time to render a single frame for 60 GHz becomes 16.6 milliseconds. So for us to render anything in a Oculus VR or a browser, this is the minimum time we should take. This is the maximum time we should take. So more than 16.6, it becomes problematic for the user. Now, for a 90 Hz, it goes down to 11 milliseconds. So it has to be rendered by 11 milliseconds for it to work properly. So the Oculus production version has 90 Hz frequency response, so we have to render every pixel, every frame by 11 milliseconds. Now the problem, you have to render everything twice. When it comes to stereoscopic vision, when we are watching anything in Oculus or in a mobile, you have to see it in two different viewpoints, so you have to render it twice from two different viewpoints. So that becomes a challenge and performance-wise when you are doing it in a browser, and especially in mobile. So is the problem really that bad? Let's try something with the Pokemon. So you can actually all open up your mobile phones, try to get into this URL, and you can try. I talked with Ron already about mobile phone part. So if you go there, you will see that this demo, while I walk around, look around, it's pretty smooth here. And this is the button, if you are in mobile, it takes you to the VR part. But if you try the same thing in mobile, you will see it works, but with quite a few lag. I couldn't get it, the mobile demo here, so hence I'm asking you if you want to try. So we'll wait a few moments. I can see a few people trying, then we'll move forward.
Just a disclaimer to bring mobile phones.
So,
and of course, everyone has to trust you as well, right?
Benefit of doubt.
and assuming people don't have mobile phones, let's go to something more textual. So this was supposed to show that it is a problem in mobile phone. We don't have a live demo. Let's see why the problem arises and what happens if we try the same thing in desktop browser. So the inherent problem is JavaScript is single-threaded. So it runs in a single thread, and there is no obvious way to actually divide the work between different CPU cores. So what can we do right now? So right now, one of our solutions becomes Webworker. So what is a Webworker? So when you have a Webworker, each worker you can spawn in a different thread, lives in a restricted thread safe environment, communicates via post message API. So there is no shared memory space. The communication between the worker happens via post message, and the workers don't communicate with each other. They only communicate to their mother worker, which gets the jobs. So message on data is copied, not shared. And this is the most important for us, that there is no access to document object model for workers. So it cannot participate anything related to rendering. But our problem was rendering. So let's see how actually worker works. So I'm going to try a live demo here. So does the worker work? Let's try. First, can you see, can you actually read the text? No, okay. Now, okay. So let's try with one worker. This is a live demo running in my browser right now, and when I run the test and wait and talk something else. So what we are trying here is that we are trying a calculation in my browser without using a worker or using one worker, and we'll see how much time it takes. So for the same calculation, it takes around 10,000 milliseconds, a little more than that. And let me try it with 4 workers. If I run the test, I didn't change the calculation size. You can see it's visibly faster, almost like 3,000 milliseconds now. So it works kind of. So when we have a calculation, when we increase the number of workers, it decreases your execution time. Since we are CS students and we like graph, here is a graph showing from the exact same benchmark for different browsers. And so we calculated the benchmark running each test for each Webworker 50 times and taking an average on it. This depends on the machine you are running, and this also depends on browser. As you can see that Chrome, Safari and Firefox, and this I ran in a MacBook, so Safari actually performed better than even Chrome. Firefox is a little behind in this. So one interesting point here was that there is a specific number of workers for which the execution time is optimal. Then even when you increase the workers more, it actually goes up a little. So that becomes because of the overhead of creating more workers than the performance trade-off from the worker that was giving us the performance advantage. So now we see that, okay, if we introduce more workers for a calculation, it decreases our performance time. But what about the calculation about graphics? Now we come to the Webworker limitation, which we talked about before, which is does not have access to document object module. We can do all the worker trickeries and all worker magic with calculation like we did, and we still won't be able to render it in the screen because of security implications. So we are going to try 2 methods we tried to circumvent this problem and try to introduce the same advantages for rendering our VR applications. So the 2 things we're going to try is off-screen canvas and offloading some of the geometry creation logics to the worker. So by offloading geometry creation calculation, I'm talking about creation of mainly triangles and polygons because they are mostly used for the rendering part. So let's try about another one. So here, what we are going to try is that we are going to try with our native Webworker implementation. By native Webworker implementation, I'm talking about it's using the workers in my browser right now. Each of these calculations will be done using 8 Webworkers, which is a number I took mostly by random. And the emulator worker test is that I'm going to use the same code base, exact code base, without using a worker, using a polyfill, which will try to think that it's a worker, but it's not using a worker, so it's one web worker. So it's just the browser without worker. And we're going to see how it performs. So this is actually an animation, and we're going to use 2 of the points to calculate that. So we have a physics rate is another animation FPS and the animation rate. So if I try for 11, and this is right now in native Webworker, so this is using Webworker right now. You see the physics rate goes from 115, then drops down to essentially it's 90, 80, 70 something. And animation rate is fixed around 29. If I change it to emulated worker and try the same thing, you see the physics rate barely goes out of 100. If I do the same thing again on 11, just goes up 100 and then it comes down. Whereas for the native, you see it's out of above 100 for a pretty long time, then it goes down when we have more animation introduced. So worker works for animation, but this was when we try to do calculation off screen. It gives us some performance improvement, not that much. Now, what about if we try to have WebGL? Now, what is WebGL? WebGL is a web graphics library which tries to have JavaScript tap into OpenGL spec, and we can introduce all kinds of document shared model, the vertex shaders, and everything. So this is very useful when you are trying to create a game or something animation inside a browser. And this is very important for us as well. So the normal question is, what happens if we try to introduce Webworker along with WebGL? So use WebGL inside a worker. And if we try that demo, what happens is, you probably can't see anything in the screen, right? That's because if I try to see what is happening behind the scenes, here you probably can see. No. Oh, yes, I can. So WebGL in Worker is not supported. So this specification is not supported by the browser right now. But what happens if we change the code inside a browser and try to do that? So I'm going to copy my slide link. Into a Firefox 90, I modify to have this and run it. So you see the worker and WebGL actually works together. You are able to introduce WebGL inside a worker. It's not supported by browser right now, but with a little change you can do that, and this improves performance. So till now we have always talked about what we can do with Webworker, what Webworker allows us to do, and the things we manage to port and run inside a Webworker, and what we manage to do with that. But what is actually a Webworker? What happens in the browser engine when you create a worker? So what Webworker is when you create a worker, it actually creates a separate instance of whole JavaScript engine. So a whole JavaScript engine, each time you initialize one, that may not be a very good idea. That is the reason you cannot go beyond 20, because there is a hard limit by the browser vendors that you should not create more than 20 web workers, because it affects your machine performance. So we need to do something about that if we have to be performant and run it in mobiles and do in a lot of scaling. That brings us to another factor. When we're talking about virtual reality, or this kind of goes to actually rendering anything in the screen or augmented reality, performance versus quality matters. So it's not just about frame per second anymore. We can have different tricks to enable better frame per second and better performance, but with that virtual reality, it becomes as long that how smooth is the response time, how fast you can respond and interact with that. So when it comes to interaction, it becomes how fast JavaScript callbacks work and everything. So we need to confirm with that as well. With that, what we have covered till now is that WebVR is a thing now. It is coming up, and this has been backed by a lot of organizations. And rendering and real-time graphics can benefit from parallelization on CPUs. But Webworkers is a viable option to achieve that end. Our benchmarks show that still they were never intended to do rendering stuff. So we can have different tricks, we can have ports, we can do tricks to enable them, but we still will have limitations. Which brings us to our future work, that eventually a better way will be needed. So the future works will be try to replace the worker logic inside the browser with Habanero C++, so that next time when we create a new worker, it doesn't again initialize as a JavaScript engine to run our JavaScript code inside it. This will enable us to make it very lightweight instead of what the present implementation has in browser engines. And so the primary advantage of this is that the application developers, mostly the people who will be writing WebVR applications, they won't notice any change because they will be calling the same spec, the same APIs of WebVR, just it will be handled differently by the Habanero C++ code. Thank you. That's mostly what I had for today. I'll welcome any questions.
I had a question about your Webworker WebGL demo. So what were the individual web workers actually doing with WebGL? Were they rendering some piece of the total canvas, or yeah, how was that?
Yeah, so each of them, so I showed, specifically the WebGL means the triangle, right?
Yeah, the triangle.
Yeah, so for the triangle, we are using a trick to actually achieve that. So what I enabled is that for each of the frames, for each of the different color frames, we are using something like off-screen canvas, which creates each different worker for each different portion. So each of them has a separate portion to handle, and then they recreate them using the main JavaScript, which is running in the main tab.
Okay, so each web worker has its own slice of a canvas, and then it renders there, and then it communicates that back to the main thread, which copies it into
For
the
that
real
demo, I actually have it in that's actually a grid. So each grid has a different portion assigned. That's not very good demo because I have them hard coded to do the work. So the grid is not dynamic sized, but yeah, that's how it works. So yeah.
Is the number of the optimal number of web workers that you have, is that tied to the number of cores on the machine, processor cores on the machine, or is it just hard limit?
I'm not 100% sure about that, but what I have observed is that it probably is based on the cores of the machine, because how many if I don't specifically say that how many workers are gonna get assigned, and so the browser actually assigns, if I say 8 worker, how many core it will utilize, that's on the browser. So the browser actually assigns that, okay, use this many number of core and for this many number of thread, so that is how it assigns, unless I specifically tell it, which we did in the nightly version. But for vanilla version of browsers right now supporting Webworker, that is on the browser. So I have no way to actually ensure which core or how much it's getting used.
I have a question about what kind of applications, what kind of devices are you targeting? So you want to use this interface on some devices itself. So now I'll come back to Abhinav's question. Now these kind of machines have very limited number of cores. So how are you going to extract best performance out of fewer number of workers on a machine with lesser number of cores?
So that's two-part question. First is that how do I actually get the optimal number of workers? Second, how do I actually ensure that this works on this? So finding the optimal number of workers, I don't have an answer to that. I know there are ways to do that, but I have not tried it with web workers. Now enabling them to the mobiles, so these demos actually will work because right now all the browsers in mobile on mostly the other applications, they don't utilize most of the CPU cores at all. And when you have anything running, and they won't be utilizing those cores unless it's specifically mentioned in the application you are running. For these, when you have, so when I had that benchmark where I changed the cores, you can actually run that benchmark in mobile, and if you change it and if you try to run it, it will run it with different web workers, it will try to utilize the codes. And you will actually see the difference, because if you try it with the benchmark mode, your mobile will get hot.
I was about to come to that, like have you thought about energy?
No. So all the VR works and WebVR and mobile, so right now everyone is working mostly on performance, getting it performant, and that is a problem, but we are not dealing with that now.
Future.
Well, interestingly, I think some phones nowadays already have 8 cores, like 4 fat,
yeah.
4 thin, and a GPU as well. So
Yeah,
it's
mine
doing
has
quite a
both.
bit for it, yeah.
What was the 2 different FPSs whenever you have the blocks?
Yeah, so blocks. Yeah, so I had one written as animation FPS, one written as physics FPS, which essentially runs as how many it's a how many blocks I have to animate per frame.
So FPS, one of them is how many images are being
Complete.
displayed to the screen.
Displayed, and how many boxes, specific boxes. So those boxes are like different colored, so I have to do separate calculations to actually create those boxes, and when they're falling, so I have to create where they're falling. So if you see the demo, so the animation FPS mostly is fixed on 30 FPS. It hardly varies, because you get the same number of frames per second when you're seeing that in the browser. But when it goes around and it does different stuff, the number of creation of those boxes, they differ. And the ability of browser to create those boxes efficiently differ. And that brings us back to the VR question. When you have a VR, you're inside a VR, you are in this room, when you are walking around, you don't want this table to suddenly like break off. Doesn't want it to be cheated. So it has to be continuously created by animation or something like that. So that was supposed to be a very small subset of that problem. You are not totally convinced. We can take it offline.
Okay.
Yeah.
Yeah, during the demo, it seemed like there were kind of like some half-second pauses that weren't reflected in the displayed frame rates. Could you explain what was going on?
Let me actually try. So, in which demo was it?
It was the falling blocks.
Oh, okay. Okay, which house shape?
When it was set, well, I noticed some more, yeah, when you set high, that, you know, it would kind of freeze partway through.
That is just my bad coding of the demo. The animation part, I apologize, that's just my bad coding.
All right, let's thank our speaker.
They usually describe it as sort of like made out of liquid.
Okay, let's get started. Tonight's the last meeting of this semester for Comp 600. We have 2 speakers today. Our first speaker is Chen, and he's going to give us a survey on database detection. Please.
I'm Chen. I'm doing my presentation about survey on database detection. So this is the intent of the presentation. I will describe what the data is and how to detect it, how to optimize it. And later I will describe my kind of work on database detection on OCR. So first, what is database? So the definition of database is here. So it means that in a parallel program, you have 2 memory access to the same location, and there's no order constraints between them, and one of them is right. So obviously, the order of those two is inconsistent. We never know which one happens first and which one happens last. So here are some hazards of this method, of these bugs. The first one is the result is not inconsistent. It will change by times you run it, you execute it. And it's also hard to detect because you need to find both of these two memory access. Otherwise, you cannot fix it. And if this bugs happens in some very important embedded system, for example, the aircraft or some radiation machine, so it's perhaps will create some disaster. So here's one very famous accident: 3 people was dead just because one wrist bugs. So this bug is pretty important. To detect this data race, we have some methods. One is called dynamic data race detection. The idea is it's use the runtime information, for example, thread creation, memory access, and synchronization, and analyze this runtime information to see whether there are any chances of this bugs happen. So here are two common methods. One is called happens before, one is called log set. So I will introduce it one by one. First one is called happens before. This is a widely used data race detection method. And the ideas came from Lampard's vector clock. So idea is, first, each thread will hold a vector clock for itself. And the elements of the vector clock will record which operation of other thread that happens before parent thread. So with compare of these vector clocks, we can see whether these two threads can run in parallel or they have some order constraints. And each memory access also need to hold two vector clock, one for reading, one for writing. And the detection method will compare them when a memory access occurs. Here is an example. For thread 0, here's a write to variable x at 4, 0. This is the vector clock for thread 0. And for thread 1, also a write at 4, 8. So by comparing these two vector clock, we know that the operation on thread 1 happens after the operation on thread 0. So obviously, this is safe. Another one is log set. The idea is a little bit different from the previous one. Like, this one is based on logs. First, it's maintain a state machine for all its variables to see how the program accesses the variable. Perhaps it's exclusive, perhaps it's shared interface only, perhaps it's shared and read and write. So we only detect database on this state because we need at least one operation is right. And for each memory access, we maintain a log set. And we try to see whether there are common logs for all of the threads that access this variable. So it means that if all the threads access this variable share some common logs, it means that all the memory access is protected by same logs. So we have some universal constraint order. If the log set is empty, then it means that data race. Both of these two have some problems. First one is not false negative. Because they can only check whether their data is in the current interlimits. We never know what happened in the unexecuted case. Another one is false positive. Happens before will not have false positive, but logset has. If you write some program with barriers and use barrier to protect the memory access, the program is correct, but logset will report that they are data race. And both of them have some. We add some overhead to the program because they need to check the runtime information. So to optimize these two methods, there are some ways. First one is called combination. The idea is simple. It's just want to combine log set with happens before. So the idea is use the lightweight set operation to replace the log to replace the vector clock for the log operation, because based on some statistics, the log operation is much more than other synchronization. And when detecting a data race, first we check the happens before relation, then we check the log set. If both of the checks are failed, it means that they have data race. So here are two tools, green and thread center, is to use this method. And although this we can optimize data race detection, but this still has very large runtime overhead. It's about 10 times to 100 times. And another way to optimize it is called filtering. So it's trying to eliminate unrelated memory access. So for example, thread local variables, read-only variables, something like that. And if you eliminate this, we don't need to check them, so runtime overhead is reduced. Here, I want to introduce one famous work called GM Race. It was on CUDA. So it's used the features of CUDA. Interesting is that in CUDA, all threads was organized into webs, and webs was executed in CMD. So we have two very interesting assumptions here. So for the intro web races, it's only happen in the sim instruction. We just need to check whether this instruction will write the sim location. And for interweb races, we need to check the order constraint. So this tool use these two features to detect it. So it has two stages. One is static analysis, it's mark variables, and another one is dynamic analysis. It will check these two types of races one by one. And because of these two assumptions, it loses no accuracy and it reduces overhead. The runtime overhead is just less than 10 times. So the third way to optimize it is called sampling. The idea is it's based on the assumption that the bug always happens in code area, which means that if the function is called very few times, we have not enough enough chance to find these bugs. So we just sampling all the code and to see whether this time we check this function call or we just leave it. And problem is that this way you need to make sure that the sampling method is effective. Here we introduce a word called light race. So it treats each function as a code region, and the sample rate will decrease when the amount of core is increased. According to the experiment, this one just had about 2 times runtime overhead, and they lose no bugs. So it's pretty effective. So all of the works before is for data race detection on common parallel programs. But recently we have another new program model called task parallel. The idea is that the program consists of tasks and data blocks, and the programmer need to indicate what is the dependency between the tasks. And all of the low-level details such as thread creation, memory management, dependency management will be handled by the online system. So this one is much more efficiency than the previous program model such as pthread. So for data race detection on task parallel, we can still use happens before, it works, but it's not use the features of this platform. And one serious problem is that it can only make sure that one interleaving is correct, because we never know what's happening in other execution paths. But with some other method, based on graph, we can detect it's more efficient, and we just need one successful execution. We know that there's no bugs in all of the interleavings. So here is an example for computation graph. This is from Java's concurrency library. Oh, sorry, this is from Habanero Java. So we have features, async is short for create a task, and future is for future will wait all of the tasks inside it. So this is the computation graph of this one, of this program, and here are 3 types of lines. The black one is thread creation. The blue one is about future, and the red one is about the blue one is about the finish, and the red one is about future. So all of this order constraint. Based on this graph, we can detect database by the graph traversal. For example, we want to see S1 and S4. Is there any path between them? If you see, obviously S1 can go to S4 by S2, so there is a path between S1 and S4. So this means that it has order constraints. So there are some works for database based on graphs. It's SP bags, ESV bags, and something like that. And this one is our group's work. So my work is on OCR. It's called Open Community Runtime. It's also a type of the task parallel library. It has 3 components: EDT, data blocks, and events. And EDT is for tags, data blocks for data, and this one is for synchronization. This is a simple C code. It will access 2 it's to array and assign values for these two array. And this is the task graph for this program. So we see that there are two tasks, two data, and there's order constraint between them. And for the data reduction on OCR, we can also use the graph-based data reduction method. First, we maintain the computation graph on the fly, and we record all memory access. And then we use the graph traversal to see where there are parallel memory access. So here is a small example. Here we have just change a little bit of the previous one. Here we have 3 tasks. All of them access array A, and you can see here that there are some order constraints between them. So for EDD1 and EDD2, there's no data race because it has paths. But for EDD1, EDD3, and EDD2, EDD3, there are no paths, so they can run in parallel. And both of them access the array A. So here we have 2 groups of data race, which is why graph traversal we can find them. So this is my current work, and we try to we try to optimize the way to construct a computation graph to see whether we can reduce the runtime overhead of this method, because graph traversal, the time complexity is n plus e, is still too high for data reduction. So we just see whether there any other chance to reduce it. This is my current work.
Questions? Okay.
I have a question. So the purpose of this is to reduce the runtime overhead of the data race detection, right?
Yeah.
So is the data race detector meant to be run on like production code, or is this just to speed up the process of debugging and finding the data races in the first place?
Could you repeat again?
So I guess my point is, if the data race detector is only there for debugging, it wouldn't matter to the end user of the program how long
This takes.
yeah. So is the purpose just to speed up debugging, or is it intended to do you run the data race detector on production code, or what's the
The idea is try to find out the data races and report to programmer. So if the runtime overhead is too high, perhaps one execution will need too much time, and you cannot get the report for debugging.
okay? So it's to speed up the debugging.
Yeah.
Can you go back slide? Okay, so actually, first I wanted to comment on Jonathan's thing. So you would never want to run these things on your production code, like
Right.
you're running it on the supercomputer, but I let you hit the main point there. It's some of these race detectors can increase the overhead by orders of magnitude to the point where it takes hours to run something for a small input, and that really kills your debugging workflow. If you have to wait 2 hours for your program, it usually takes 2 seconds to complete the system work. But okay, so my question is, you explained the complexity for this on this slide, but I didn't really follow, so I was wondering if you could elaborate a little bit on the time complexity. Where do you?
For this one, we use graph traversal, and if you want to find whether there are paths between one node and another node, time complexity is n plus e, right?
Oh,
Yeah. So each time you have a new memory access, you need n plus e to check whether there are data races. For any pair of two nodes.
for each memory access, so it would be number of accesses times
Oh yeah.
n plus e.
No. One is n plus e, and we need to record all of the previous memory access and check them each of them once.
So what's the total complexity? Is it proportional to the number of accesses and the size of the graph, or is it just the size of the graph? Or is it
Both of them. First is the size of graph, second is how much memory access to the same memory location.
Yeah, one thing Rishi showed in his RV paper, which he may have presented in Comp 600, is to do a shortcut and use the task hierarchy before you start the graph traversal, because you can use the tree structure, least common ancestor algorithm first. But in the worst case, it's what you said, for every conflicting memory access, you may have to do a full graph traversal. That's the worst case.
Okay, so it would be number of accesses times the complexity of traversing the whole graph.
Yeah.
Okay, yeah, that doesn't sound good.
So the slowdown was a factor of, in practice, was less than a factor of 10 for Rishi's work in the future.
Other questions? Let's thank our speaker again.